Okay, so you've definitely seen these things, right? On old ships, maybe in movies, you've got these two big, mysterious-looking balls. One's usually red, one's green, and they're just sitting there on either side of this brass thing. Have you ever actually stopped to wonder what they're for? Well, let's get into it.
Yeah, if you've ever set foot on a ship, you've probably noticed this weird setup somewhere on the deck. And no, they are not just some quirky decoration, and it's not just to tell port from starboard. The truth is, without them, one of the most fundamental tools for navigation would be completely, totally useless. So this entire contraption, the whole thing, is called a binnacle, and its one and only job is to house and protect a ship's magnetic compass. You know, one of the most vital instruments in all of navigation. You'll usually find it way up on the highest deck, sometimes called the Monkey Island, so it has a clear view, with a bunch of mirrors so the crew can read it from the bridge down below. Now, a magnetic compass is just a brilliant, simple device, right? It's basically a tiny magnet floating in some fluid, and it's so sensitive, it just naturally lines up with the Earth's magnetic field. This worked perfectly on old wooden ships. But, when we started building ships from thousands of tons of iron and steel, a huge problem popped up. The ship itself becomes a giant, unwanted magnet, creating its own magnetic field that just messes with the compass completely.
To really get how sailors cracked this problem, we've got to break it down into two parts. So first up is tackling the ship's permanent magnetism. This is what's known in the business as hard iron.
So let's look at the key difference here, because this is crucial. Think of hard iron like a regular fridge magnet. Once you magnetize it, it just stays that way. Soft iron, on the other hand, is only magnetic while it's sitting inside another magnetic field. And honestly, understanding this distinction is the key to solving this whole puzzle.
So how does a ship become a permanent magnet in the first place? Well, during construction, all that intense heat from welding, the constant shock of hammering, it literally forces the magnetic particles in the ship's hard iron to all line up with the Earth's magnetic field, right there in the shipyard. The ship is basically being forged into one giant permanent magnet with its very own north and south pole.
And this permanent magnetism, well, it creates a predictable error. So, for example, if the ship's bow happened to be pointed north during its construction, it gets a permanent north pole. Now fast forward, and that same ship is sailing east. Well, its own magnetism is going to pull the compass needle over to the west. This error has a name. It's called deviation, and while it changes depending on the ship's heading, it's always consistent. So how do you fix a predictable problem that's being caused by a permanent magnet? The answer is actually beautifully simple. You fight fire with fire, or, in this case, you fight a magnet with other magnets.
And here's how it works. See? Inside the binnacle, there are these little slots for small corrector magnets. By placing magnets that run fore and aft and others that run side to side, and then by adjusting how close or far they are from the compass, you can create a counterfield that perfectly cancels out the ship's permanent magnetic field. It's really clever.
But wait, that only solves the horizontal problem. The Earth's magnetic field also has a vertical part, so the ship picks up a permanent vertical magnetism too. Now, this isn't a big deal when the ship is perfectly level, but the second it starts to roll or heel over, that vertical field starts messing with the compass. And the solution for this is just as elegant. Hanging right below the compass is a container, and it's literally called the healing bucket. It's filled with a bunch of small vertical magnets. Their one and only job is to counter that vertical pull and keep the compass steady, no matter how much the ship rolls from side to side.
Okay, so we've managed to cancel out all the permanent magnetism. Awesome. But that's really only half the battle. Now we have to face the much, much trickier soft iron problem, a magnetic field that is literally never the same from one moment to the next.
Remember how we said soft iron only becomes magnetic while it's in another magnetic field? Well, think about it. As the ship turns and sails, the soft iron parts of its hull are constantly being magnetized and demagnetized in different ways by the Earth's field. This creates what's called an induced magnetic field, and it is constantly in flux.
And that is the real head-scratcher. You can't use permanent magnets to fix a problem that's changing from second to second. So, how in the world do you correct for a magnetic field that just won't stay still?
And here it is, finally, the answer to our original question. This is where those two mysterious balls make their grand entrance. The solution is nothing short of ingenious. To fight the induced magnetism from the ship's soft iron, you don't add more permanent magnets. You use the exact same material that's causing the problem in the first place, soft iron. These are called Kelvin's balls, named after the physicist Lord Kelvin. And here's the genius part. Because they're made of soft iron, the Earth's field induces magnetism in them, just like it does in the ship. But by placing them on either side of the compass, their induced field ends up perfectly countering the ship's induced field. It's a brilliant, self-correcting system that works in real time.
So what about the vertical part of that induced magnetism, from things like the funnel or the masts? Well, that's handled by another piece of soft iron, called the Flinders bar.
It's a vertical bar placed in front of the binnacle, and it does for the vertical axis exactly what Kelvin's balls do for the horizontal. And there you have it, the complete, elegant system. For every single type of magnetic interference, whether it's permanent or induced, horizontal or vertical, there is a specific, ingenious corrector designed to cancel it out perfectly.
But as brilliant as this whole system is, it is not a set-it-and-forget-it kind of solution. Out there in the real world, the work of correcting a compass is never truly finished. A ship's magnetic profile is always changing. Loading up new cargo that's magnetic can alter the field. Any kind of maintenance that involves welding or hammering can actually change the ship's permanent magnetism. Even just sitting in a new port in a different part of the world for a while can have an effect. And all of this means those correctors need to be constantly fine-tuned.
This is just the day-to-day reality for navigators. Even with all of these corrections, there's almost always a tiny little bit of error left over. So sailors have to swing the compass regularly, which means comparing its reading to known headings, and they keep a super detailed log of the errors on every single watch. That way, they always know exactly how far off their compass is at any given moment. And all this leaves us with a really fascinating question. We live in an age of GPS that is accurate down to the inch. All this sophisticated electronic navigation. And yet, maritime law still requires every single commercial vessel to have one of these fully corrected 19th century magnetic compasses on board. So why do you think that is? Why does this elegant, completely analog solution remain an essential, non-negotiable tool for every modern ship at sea?